So we're talking about R and SAS, using R and SAS for this class, and so as time has gone on, I've been trying to incorporate R more and more. It still probably seems like it's more SAS based, and that's probably true. But I've been adding R into the class and into the course notes and the slides as much as I can, and it's still a work in progress. But I just wanted to highlight a few things. If you are using R relative to SAS, so I am sharing this. So, okay, so let me just get this down to that size there. Okay, so basically there's two packages that I know of to do mixed models in R, and they are the LME4 and the NLME packages. And maybe you guys are already familiar with this. So the LME4 basically allows you to do random effect models. Okay, so you can add fixed effects, you can add random effects, but it doesn't allow you to specify the error covariance structure. And from what I can tell, it actually works pretty well in terms of, you know, model fits, it converges, you get accurate estimates. So it seems, I think out of the two, this is actually the best one, but it doesn't let you specify the error covariance structure. The other package is NLME for nonlinear mixed effects models, and linear mixed effects models. LME is a function within that package. So real briefly, this data set, so if you have raters or judges that are judging subjects, we talked about one example, like Dancing with the Stars, just as a fun example. If you have three judges, and this one's going to be harder to draw on, I think, but let's see. Give me just a second. I'm just going to grab the Word version of this real quick. All right, so I'll just resize this a little bit if I can. That's okay. Not down here. Okay, so we have this example. We have cross random effects, and what that means is if we have a judge 1, 2, and 3, and we have subject 1, 2, up to n, you can think of it on a grid like this. So every judge evaluates every subject. Okay, so like on Dancing with the Stars or any show like that, you have dancers and then each judge gives a score, right? So that's the same kind of situation here. And we'll talk about this actually more today, cross versus nested factors. This would be cross, where you have all possible combinations. And so if you run the proc mix code for this, you would put in subject and rater as separate random effects. And in this case, we just have an intercept. So it's a actual random effects model. There's only a fixed intercept that we're going to fit. If you're to do this in R, then you would call the LME4 package, and then it would be the LMER function. And this is the code, is just one line essentially to write for that. And here's just a little bit of output for that. And you can see that it matches up. The thing is, R reports standard deviations and SAS reports variances. So, you know, when you first look at it, it's like, why are they different? Well, these are the square roots, right? These things are the square roots of the variances over here. So what you get in the default output's a little bit different, but you can tell that it's the same model fit. Okay, that's if you have just a true random effects model. And then I have just a quick example to show you what do you do if you have, random or repeated or combination. What do you do in that case? I would use the LME function again. If it's just random effects, you can probably do the LMER within LME4 is maybe your best bet. But here I'm showing some combinations of this dental data set, which is a lot like the Ramus data. Not exactly, but it's very similar to it. So let me just go real quickly to the output because I just want to highlight a few things. So if you have a random intercept only, we know how to do that in proc mixed and SAS. If you use the NLME package and the LME function, then this is how you would specify. And again, we can, just looking side by side, there's a few differences. In R, you have a log likelihood, and in SAS, it's a -2 log likelihood. But you can tell that it's the same. And there could be differences in terms of, the penalties. That's the comment I'm giving here. But essentially, whether penalties are given or not. You look at the fixed effect estimates and they're the same. So you get the same results. But again, in R, we could have done this. We could have used, in this case, LMER from the LME4 package, okay? Because we just have a random effect where we don't specify the error covariance structure. The second one, I have just a repeated and not a random. So we're specifying the error covariance structure, but not adding random effects. And what you do in that case, and you guys, some of you already, I've seen this, that you've done this already, use a GLS function, and that stands for generalized least squares. And I do actually talk about these methods in the course notes if you're interested in that. It's a generalization of the least squares principle, and it allows you to specify different error covariance structures essentially. And if you try to use LME here and you just have the error covariance structure but not random effects, then it doesn't work. So when you just specify the error covariance structure but you don't have random effects, GLS is your best way to go within the NLME package. And again, with this data set, you can see that we get equivalent results, although the way the results are presented may look a little bit different. Okay. Then the last approach is if you have both. If you have a random and a repeated statement. In this case, again, you use the LME function within the NLME package. And this is how you'd specify, we have a random effect, and then we also have the error covariance structure that we need to specify. And again, you can see that we get the same results, maybe presented slightly differently. This is the one thing I mentioned last time, though, about R, is for more complex data sets, this LME function doesn't always seem to yield accurate results, okay? And I haven't, studied exactly why that is, but I feel less confident with that in general, except for maybe, smaller data sets or things that can be verified in SAS. So, you know how R is. It's like it's continually being updated. So I imagine that we'll get to the point where we have decent mixed models where you can specify both. But I don't know if this is the reason why. We were talking last time, I think Carrie brought up the question why, you know, that somebody had told you, well, be careful about adding both, or you have to have a good reason to do it. Well, yeah, I mean, that's always the case for any model. You need to be able to justify the model you're doing. I specify a lot of models that have both random effects and non-simple error covariance structures. And we're going to see more of those. But I would say right now, I'm more confident in using SAS for those types of models. Any thoughts or questions you guys have on software? You know, so we talk about SAS and R in this class. There's Stata or Stata, I still don't know the best way to say that. I've used that before, and that's a good software as well. That's not something that I see a lot used on campus, but you see it in literature. You'll see Stata code, you know, in papers and stuff like that. But clearly R and SAS are, you know, for statistics are the ones that you're going to see the most. So the rest of those, I'll let you guys read through that. It's not something I really plan to talk about too much. But, you know, if you want to use R, that's fine. You know, even if I give you a little bit of SAS code and it's like you want to figure it out how to do it in R, that's fine. Some things will be easy to do. Other things may be more challenging. So a good example is Kronecker product structure. That's another one where in R, if you look it up, you see a lot of stuff on Kronecker product structure in R. But actually fitting a mixed model with the Kronecker product structure, I still haven't seen an easy way to do that. If you guys find out how to do that, whoever does that, I'll give you extra credit, because that's like, and I don't want you to throw me some code that I have to write it myself. I want you to write it, and you give me the code that will fit the mixed model with the Kronecker product structure. Then I'll give you extra credit. But I've seen, you know, that function or package or whatever, people have said, oh, here it is. But I want to see you actually write it out, you know, write out that mixed model and how that would look for the homework question. That'll be worth some points, so if you can do that.
Hey, Matt, that's actually a pretty easy thing to do in R, and I can send you a code.
Okay, send me the whole thing, because I've had, like I said, other people said, yeah, here it is. And then I had to like work through it.
Okay,
so,
I'll send you the whole thing. It actually is pretty easy.
Okay. Looking forward to seeing that. So let's get into the notes for today, which is nesting and crossing. So we're going to talk about, you know, what those terms mean in statistics. You hear those terms used a lot. We're going to talk about hierarchical models and more complex data structures and how we model that. So there's related material in the course notes that you can look at. So the term nesting can be applied to many things, including the design structures, the treatment structures, factors, data, or models. And they could be different. So like you could have crossed factors, but nested data. So you need to distinguish how and when you're using those terms. Okay, so we're going to first talk about, where did I say? Writing pen. It disappeared on me here. This can't be too far. I do this at home all the time, and my wife's there to tell me where it is. This is really weird though, because I've just been sitting here. I didn't get up. Okay, here it is. All right, so factors A and B are crossed if every level of A occurs with every level of B. So like the myostatin data, that's one example where we had two groups and we had 3 times and you saw each combination. So if you can make a grid with this, right, then like we did with the cross random effects, it's the same principle. So these factors A and B are crossed. So B could be time, A could be group, or vice versa. So you see every possible combination. And so that's the best way to consider that. Factors are nested when the levels of one factor occur with only one level of another factor. For example, consider an experiment. Consider an experiment designed to determine the effect of school and instructor on standardized test scores of kids in elementary schools, where each school has a unique set of teachers. So one teacher is going to be in each school, right? And you can evaluate, not necessarily, it's not necessarily totally their doing if the kids do well or poor, but if you're looking at the test scores for the kids in their classroom, the teacher's only going to be within one school. So the kids are nested within a classroom and teacher for each school. Whereas factors are going to be crossed if you have the last week we talked about an example where we had day and we actually took measurements of time of day, morning, noon, evening. And if those have the same meaning, then they're considered crossed. If they don't, then they're nested. So with that example, what would we need to ensure to make sure that those are crossed factors for this example here? Or when would they be nested? You can look at it either way.
Like if every day had every time of day in it?
Then they would be
crossed.
Okay, so explain that to me a little bit.
Like if you have day 1, it has morning, noon, and evening. And then you also have day 2, like every day has every morning, noon, and evening.
Yes, yeah, that's right. Right, so every day has every morning, noon, and evening. But what about those definitions, morning, noon, and evening?
They'd have to be like consistent across all the days.
Exactly. So like when we say morning, noon, evening, that could be a lot. That could mean a lot of things, right? But if it's the same time, like if it's 9 a.m., then it would make more sense that they're crossed. So if we say 9 a.m. and we say noon and we say 5 p.m., then it's consistent, right? It's the same time. But if we just say morning, well, we're not distinguishing like between 5 a.m. and 9 a.m. and the measurement, what you observe could be a lot different. So in this case, I would say if we had this kind of situation, and this is time of day, this would seem like a crossed factor situation, right? Where we have consistent times, but So I'll say, but what about morning, noon? If we say noon, I guess we're implying that it's, you know, high noon, but midday, if we said midday or something like that, it would be, so this one's not clear. We'd have cross factors. So the answer like depends on your design, and not just their design, but what actually happens. And it's the same situation. Like there's studies where, you know, you do clinical trial or observing subjects over time, and they're supposed to report to the hospital after 1 year, after 2 years, after 3 years. But sometimes they come in a little bit off of that, right? So they'll come in at maybe 8 months, or they'll come in, you know, typically they'll come in later, you know, maybe 14, 15 months. And so even if you have a design that says this is what we're going to do, sometimes in practice, things work out a little bit differently. So in this case, maybe if subjects are self-reporting, maybe they won't always hit 9 o'clock, you know, maybe it'll be 8:30 one day, 10 another day if they're, you know, reporting a certain measurement. So now we're getting into an area where it's like, well, how close does it have to be for it to be crossed, right? Is 8:45 close enough to 9? This is where you have to sort of exercise some judgment about the design, and then how actually the data were collected, and make a decision about what you actually have, and then how you treat those, whether they should be nested or crossed. Okay, so there's some, you know, kind of, you have to use your judgment, I think, is one of the lessons in this.
Why couldn't you just do day 1 with morning 1, and then day 1 with morning 2, and then day 1 with morning 3, and so on? And then again, across all of the time points.
Day 1 and morning 1, day
1 and morning 2.
in terms of what are you saying?
In terms of the Kronecker product.
Oh, well, you could do that, but the Kronecker product, what you're assuming is that the mornings, they have the same definition across days.
Right,
That's what you're
sure.
assuming with the Kronecker
Sure, but
product.
if you look at the matrix that you drew, you only have day 1 with morning, right? So it would be day 1 with the first morning. But what I'm saying is that the mornings are now not, if they're not equivalent, then you'd have a morning 1, a morning 2, a morning 3, and so on.
Yeah.
And then you'd cross every day 1 with all of the mornings.
I guess I'll have to talk to you more about that design, because it sounds like what you were starting to say sounded more like a nested situation.
Mm-hmm.
And then you switched over back to crossed. So
Okay.
talk to me after class about that. I'm curious about your thought on that. So basically what I'm talking about now is you kind of consider it one way or the other. Either you consider it crossed or nested. And essentially the difference is that we're not, if we have time of day consistent, if the morning, noon, and evening have consistent meanings, then it makes sense to talk about a main effects of time of day and main effects of day. And if we don't have that situation, then we have time of day nested within day, right? And I'll show you some data and how to consider that either way here in a second. But again, this just kind of summarizes a couple examples. The myostatin data, those are cross factors because every level of one factor occurs with every level of the other one. The nested situation, we have in school A, you have teacher 1 and 2, so they have occurrences there marked with X, teachers 3 and 4 in school B, and so forth. So that's teachers are nested within schools in that situation. As far as notation, this is sort of what we borrow from SAS. B nested within A is how you'd read that. And sometimes you also see it on subscripts. So like you may see the situation where J is nested within I, so that, repeated measure J nested within I subject, or you could think of it as a subject nested within a school or clinic or something like that. So this is the example I'm going to get to, going back to the morning, noon, evening thing, and whether or not we should consider it as crossed or nested. So we have 3 times of day, morning, noon, evening. The question is, those have consistent meaning across days? So we have 2 units of time. We have day and time within day. So if we can consider them as cross factors, then we can write the model this way. Okay, and again, we're considering that grid essentially, and you could also add in the interaction. Okay, and we commonly do that in our models. We have day, time, day by time. If you've established that that there's no interaction there, you can take that out. But you can still get specific time by day combinations from the marginal estimates there. Okay, so you can see here we have day 1, 2, 3, time 1, 2, 3, or you can think of this as the morning, noon, evening. Okay, now if we cannot consider morning, noon, and evening to have consistent meanings across days, then the way we write our model is we have day as an effect, and then we have time within day. You could have actually put time by day and you get the same thing. Okay, so you could have written this as time by day here. You'll get the same thing. But the main thing that you don't see is time in this model, because time, the meaning for time changes across days. So we don't have that term in the model. That's the main difference. So you can see we have day 1, 2, 3. We have then we have time within day, and we have so we would have morning, noon, evening, and then the same thing, but because of the fact that they may have taken their morning measurement, like one day it could have been at 9 o'clock and the next day maybe it was at 7 or something like that, then we're allowing separate estimates for each day for those morning, noon, evening times. Okay, so our effects are for day and time within day in that situation.
Question.
Yes, Benjamin.
So how do we explain to someone who really wants to see the main effect of time? Because, for example, you realize in some models, they want to see the base, like the main, before you go to the interactions. Like they say you can't have a higher order without the base variable. So how do you explain that to this person?
Yeah, I mean, I think you could still, you could probably still do a test, and extract that out. But you just have to be careful because, you're averaging over things that are, you're averaging over apples and oranges, right? So yeah, I guess you have to explain to them that the design led you to model it this way. Now it's true that what you're saying, Benjamin, that's true in general, is that we don't recommend taking out a main effect if there's an interaction term, which essentially that is, right, time by day. But I've written it, you know, clearly here so that we're showing that we're dealing with the nested model. So I think the answer to that person would be the design has led us to write the model this way, and it's a special case, and that's why we're not doing it like we normally teach, and you know, which is to always include the main effect when you have an interaction. So the design led us to that.
Okay,
I have
thank
a
you.
question, Matt. Oh, sorry, Benjamin.
Yeah, I think it was done. Go ahead, Jonathan.
Yeah, so I was wondering, what you're doing here is you're stratifying by time, correct?
In a way, we're still getting main effects of day.
Right.
So
You
we're
still
not
get the main
stratifying
effects of it, but not the time because you're stratifying by time.
Mhm.
Okay.
Yeah, in a sense, we're doing that when we're getting those separate estimates over here. When we're getting these estimates. Yeah, I can think of it that way. So I ran it both ways, right? But really, which one's the right one? It's not the one that you get the best p-values, right? And you know, maybe we smile at that. We're like, ah, that's funny. But your client, that's the way they think. they look at the p-values. I like that. That looks good. But we have to go with, what do we go with? We go with the one that matches, that's most appropriate for the design, right? And the problem though is that it's not clear cut. Like I said before, what is consistent meaning? In this case, for morning, noon, evening, what is consistent meaning? You know, because maybe 8:45 is close enough to 9 that you can consider it the same meaning. But how different do the times need to be for you to consider them differently? So there's some judgment involved with it. But you want to try to write the model that's appropriate for the design. And if the times are close enough, then maybe doing the crossed approach is sufficient. But
Hey,
if you
Matt.
have information like suggesting that, you know, they took at 5 a.m. one day and then 10 another and so forth, then you want to maybe consider the nested approach. Somebody going to say something?
Yeah, I have a question. So if it's not close enough and you do use the cross, what is the assumption that you're making? What are you concluding that isn't true?
You're concluding that the factors are not crossed. That's all. That's the only thing I can
But in
think
terms
of.
of the estimates and the model and and I guess how you start interpreting this model, what is the danger of crossing factors that aren't actually crossed?
That's a good question. I think you're losing information. You know, it's kind of like when you have a situation where you have main effects in an interaction, and there's significant interaction, and you take that interaction out of the model. It's kind of similar in the sense that, you know, you're losing information. You can still get main effects, right? You can still run that model. It's not a wrong model. And I think it would be a similar situation, but you're losing information. You're averaging over things that don't have the same meaning. So I would say it's not incorrect, but you're losing information, would be the way I would think about it. So again, you know, you want to write the model that's correct for the design. And in some cases, it's not obviously one or the other. It's a matter of degree. And so we need to use some judgment when we do that. So we could also consider nesting as it relates to the experimental units. So nested subjects would be an example of that would be if subjects were assigned to treatment and they continued without, throughout the whole study on that same treatment, then subjects are nested within treatment, right? So that'd be like a parallel design. So I also make a comment here. This is typically not done. I mean, usually subjects, and I would recommend this, that if you have a study or experiment, you want to have a unique ID, whether subjects are staying within treatments or not. It's just not good practice. It's just not smart to repeat IDs for different subjects, even if they're nested within groups. But another reason why we would want to use this type of notation, especially if you just have random effects. We talked about this with denominator degrees of freedom. This becomes useful because it will give you the correct denominator degrees of freedom. So I'll make just to make a note of that. Used to get better, I don't know what the word is, better DDF values when random or the random statements used. So that's specifically for SAS. Okay. Nested versus cross random effects. We talked about the crossed subject and rater, where every rater saw every subject. And so those are cross factors. If you have a situation where you have different schools and teachers are nested within schools, then the way you would write that would be like this. Okay, you'd have school, and then you'd have teacher within school, and that indicates nesting of school and teacher. Okay. So the way you write nested models, if you have hierarchical, so this implies nesting here. It sounds fancy, doesn't it? It's a hierarchical linear model. It's like, wow, that sounds really complicated. It's just models written for data or factors that may be nested. And so this notation that we have on this page just distinguishes the different levels in the hierarchical model. So if you have this first situation, we have the way we'd normally write it would be Yij, so subject I time j is usually how we think about it. And we have just write in what we have here. So we'd have beta naught plus U0I, and then we'd have beta 1 Tij. So that's how we normally write it. So what we're doing is we're distinguishing the repeated measures part versus the subject part. Okay, writing those two things separately. In practice, I don't really do that, but this is just conceptually allows you to think about the different levels. And then if we had the difference between that one and this one is that we just added a random slope for time. So here we just have beta naught plus random intercept. And then we have beta 1 plus U1I and time, that's our time variable. And we would just, normally we would write this out. So we'd have the fixed effects piece. So this would be beta 1 Tij. and then we'd have our random effects piece. Okay. How would the Z matrix look relative to the X matrix for this example? So think about the X matrix, right? What are the dimensions for the subject level X matrix here? How many columns would you have?
Would it be 2 columns?
2 columns, yes. And the Z matrix, somebody else, how many columns did you have in the Z matrix?
Still two. Well, for
2.
each subject.
Yeah. So they're actually the same in this, for this example. The Z matrix would be the same as the X matrix. You'd have your column of 1s for the intercept, right? And then you'd have column for times, right? And X and Z would look the same for that example. So the slides here, the next several slides are just talking about different examples for hierarchical data, which could include repeated measures. So example, healthcare costs for individuals. So they could involve repeated measures, but I guess my first point on this slide is that they may not involve repeated measures as well. So healthcare costs for individuals with different health insurance providers. So level 1 model would involve the subjects, so for the outcome, I denotes the provider and J denotes the subject. And the level 2 model would involve the provider. So the level 1 is the smallest unit. And then the level 2 is a bigger unit, level 3 is a bigger unit, and so forth. And I show how you can think about the models for level 1 and 2 in that case. For the standardized test data, if there is 1 response per teacher, level 1 model would involve the subjects within schools, and the level 2 model would involve the schools. And again, just thinking about, how do you just think about the level 1 is a lower number, so that's the smallest unit that you have. Then level 2 is bigger, level 3 is bigger, and so forth. So for the 3-level hierarchical linear model with insurance data, if we're taking measures over time with that, and each subject has a different provider, then the level 1 unit is a repeated measure over time, and that's nested within a subject. Level 2 unit is a subject, and then the level 3 unit is the provider. So you can see we're getting a bigger experimental unit as we get to a bigger level. So although we may say repeated measures are nested within subjects, it's possible that the factor associated with repeated measures, for example, time, is crossed with subjects if we're looking at the subjects at the same time points, right? So again, the way we consider the terms here depends on whether we're talking about factors or whether we're talking about data or something else. So they may need to be defined separately. So for this example, if we have a design where we're looking at, let's say, 2 months, 4 months, 6 months, and we take those same measurements on subjects at those time points, then 2, 3, and so forth, then those factors are crossed, right? Even though the measures, the repeated measures, are nested within subjects. So the data are nested, the factors are crossed. Some more examples here. I'm gonna jump this unless anyone has questions. So these are just different examples where, you know, the largest unit could be like a hospital or provider. The middle unit, you know, might be the subject, and the smallest unit, the repeated measures. You could also have a situation where you have, you don't have repeated measures, but you have 3-level data. So, so for example, you could have subject as the smallest unit, and then you could have, well, why don't you guys tell me, give me an example where you have 3 levels, but you don't have repeated measures. Can you think of an example?
Like subject, county, state.
Yeah, that's a good one. So the middle unit is county. What county are they in? And then the largest unit is state. That's a good example. And I'll let you guys read through these other examples. I think I thoroughly, I talked about a lot of those, so you guys can review those different examples. So nested data may or may not involve repeated measures, okay? We're gonna talk about a data set here where we do have repeated measures on subjects. And the motivation for this is that this was actual data collected on subjects. It was part of the EPA study done here at National Jewish. And there's a school here, I probably mentioned this. It's now the Morgridge Academy. It used to be the Koonsberg School. It changes based on how much money you give. if you can give them a lot of money, they'll put your name on the school. And so Morgridge, I guess, gave a nice donation. And so it's now the Morgridge Academy. And it's a K-8 school here at National Jewish. And it's good for these kids because they, most of these kids have asthma or some kind of lung issue going on, but otherwise they're healthy kids. The employees here interact a lot with the kids. They have a reading program where you can go read, you get a reading buddy and you can read to the kids and stuff. And so there's good work that they do here to keep the kids in the schools interacting with the staff and faculty. But these kids, they're here because of their asthma, and it provides a way for them to be supervised, you know, get treatment if they need it. But otherwise, it's just like a regular school. It's a relatively small school, but they have classrooms. They actually have a gym. They have a pool, a number of things here. And they were involved in this EPA study. So we were looking at the health of these kids over time and how their health related to air pollution in the city. So we came up with some good research and some interesting results based on this 9-year study. But one of the things that we realized was that the kids enrolled, a lot of them came from the same family. So there's siblings involved here. Now, one of the things we talked about early on is how our general assumption for mixed models is that we have independent subjects. Well, if you have siblings, that kind of raises a question, are they really independent or not? And even if they're not independent, you would think that if they're siblings, there's some kind of correlation going on. So if one kid tends to have higher values for an outcome, because of the fact that they're siblings, that may increase the chance of their brother or sister having higher outcomes or lower outcomes. So it's something that we should probably at least look at, right? Is whether this dependence between siblings may impact the data. So for these study years, 2001 to 2002, there were 48 subjects from 40 families. And in the following year, academic year, there were 57 children from 52 families. But in both of these years, there were never more than 2 kids involved from the same family. So we can still fit a mixed model with this, even though kids are, you know, we want to look at family now instead of kid. So we define a larger unit, and that unit is family. And now we assume that families are independent of each other. But we are allowing correlation between kids within a family. We at least want to test for it to see if it's something we should be concerned about. So the way we write the, some of that I've just, what's on the slide I've talked about. And this issue comes up a lot, like in medicine. Like, you know, we learn about the methods and that our methods really apply for random samples. Well, in medicine, honestly, there's not a lot of times where you actually have a random sample. You get people that agree to participate, you know, so a lot of our data are self-selected, and you can test the same assumption if you have issues of, you know, having the same family members or things like that. You can test in a mixed model. So we have the level 3 unit is family, the level 2 unit is children within families, and then the level 1 unit, we're going to take measurements over time, and that's the level 1 unit. So we have 3-level data here. We're measuring LTE4. It's a biomarker in the body that has been shown to be associated with inflammation. So we got urine samples from the kids same time each day, and within that we were able to measure this the level of LTE4 in the sample. And so if we saw that that was higher, that would indicate to us that there was some inflammation going on with that kid on that day. So some of the other variables that we have as predictors, whether or not they had a cold at the time, temperature, pressure, humidity. Air pollution was also one, but I think in the model I'm showing you, I don't have that particular predictor in there. So here's our model. I am going to include 3 indices. H is going to be the index for family, I for subject, and J for time. And so we have continuous predictors for date, cold, temperature, pressure, humidity. Date, this is essentially a linear time trend, right? Because it's a continuous variable and we have a coefficient in front of it. So we're just testing for a linear trend in the LT4 values over time. We have the random intercept for, so this is our random intercept for families. And then this is the random intercept for kid within family. And then we have our error term there. Okay, so for the repeated measures, I'm going to specify AR1 structure for the error covariance structure. And the SAS code here, this would be one where I'm not sure if R would work. We could try it, but if we did use R, we'd probably use the LME function. We'd try that. For SAS, we use proc mix, and we have the family, the highest unit, and then we have ID within family, and then to measure or to account for repeated measures over time, I have the AR1 structure. Now here's a good question for you guys. What if I didn't include the repeated statement? Would we still have a would we account for repeated measures on subjects if we just had that random statement and the two nested effects there? Would we still account for repeated measures? This is a question that's a good one because it helps you understand where the modeling the repeated measures comes into play. Carrie?
I think it's yes, but it would just be assumed to be the same over time. Kind of like the compound symmetry with just one intercept. You still account for it, but it's just equal.
That's right. So because we included ID within family, that actually is going to induce that compound symmetric structure on the subjects. And similarly, what about this family? What does that induce a structure on? If you're thinking in the same line of logic here, does that induce a structure between families or something else? Well, so what Carrie said was having the ID within family induces a structure on the repeated measures, which is the first level, right? Repeated measures is level 1. The ID within family is a level 2. So what we're saying is it induces a structure on the next lower level. If that's true, then what is adding family going to induce a structure on?
Kid.
On the kids within a family, between kids within a family. So this family, this will induce the correlation structure between kids within a family. And this one induces a correlation structure between measures within a kid. So why would I include the repeated statement then, if this is true?
You can specify then AR1.
Yeah, which is better for longitudinal data, right? That's right. So this is this one is more time sensitive correlation structure for repeated measures within KID. Okay, so we actually have two things going on to combine together for the repeated measures within a KID. So you actually, one of your homework questions this week is, what does that structure look like, and how is it different? You know, the one that adds a random intercept for kids and we induce a compound symmetric structure, and then you add on to that the AR1. What does that structure look like? Well, you know, you figure that out using that V equals Z, G, Z transpose plus R. And that's one of your homework questions, is to show what that looks like. And then what does that allow you to do that just having the AR1 can't do on its own?
Matt, just to clarify, you're saying that without the repeated, both the family and the ID family would be the compound symmetry on each of those pieces?
Yes. Yeah, so, you know, but you have two levels to it, right? You have the family level and you have the kid. So, but it's the same principle. You're gonna, like, let's say you had 10 family members. You know, that's not the case with the data, but if you did, you're assuming the same level of correlation between family members? Yeah, good question. So I had another comment here. If you wanted to add a random slope for kids, that's, you know, you can do that, but for now we'll consider this as probably complicated enough with the 3-level data, but something that, you know, you guys probably can understand. So we have a mixed model that has nested random effects. It also has a repeated statement in it.
Can I ask a question?
Yeah.
So the only way that SAS knows that that random family and ID random are intercepts and not slopes or any coefficient is because you don't have the backslash subject ID on the other side to say that this is a coefficient within a subject.
Yeah, so I mean, there's 2 approaches you can use with the random statement. You know, we learn about the random intercept and then the slash subject equals ID. That's one approach. The other approach is to just say random ID semicolon. Those will give you the same model fits, but they are actually a little bit different because one considers the subject level model. It's like if you say subject equals ID, you're creating a subject level G matrix. And if you just say random ID, you're creating a complete data matrix. Now the models, the underlying models are the same. It's just kind of the numerical way that you're approaching it differs a little bit. But when you have something like family or center or some other factor that other than subject, then it's more common just to say random family. But yes, that's what it does. It'll fit a random intercept for that factor. So did that answer your question? It's really because we have the nested situation here, it's easier to write it this way than the way we normally write, which is random intercept slash subject equals ID. You know, because here, obviously there's 2 levels, right? There's 2 levels.
Yeah.
We have the family level and then we have the kid level.
If you did want to also put a random slope in, like in your little box, or
Then we'd be forced to do it. Yeah. And you could do it, Carrie, you could say random family, and then in a separate statement, you could say random intercept subject equals ID, and you'd get the same model, but it just simplifies things to have it here. But if you do the random slope, then yeah, then you have to add that extra random.
and you can just make that a separate random station.
Yeah. Yep.
Hey Matt, I have a quick question. So
Yeah.
far we've been talking about nesting, and both our random effects are categorical. What happens if you want to model time as a continuous variable and you'd like to nest within the time?
Then it's really complicated. Well, give me
What I asked.
no, yeah, no, it's a good question. Let me get back to you on that one. You know, we can do that. So let me just make a quick note of it. So if you have continuous time and time is nested within
Within day or whatever it is, day or month or year.
Okay. Okay, that's good. You know, you teach this course like this 13 years or something like that. And it's what's really cool is that it's never like you're done, right? It's never like you're done with you know, learning the material and you teach it. There's always new stuff, new questions I get, which is great, and it kind of keeps everything fresh. And then we have new methods that are derived, you know, like the spatial temporal methods are new. And so there's new ways to model correlated data. Things never stop. And as students, this is one thing, this is kind of an aside, but really what we do is, you know, you learn, you're in your classes now, but you get to the point where you're gonna be, you know, you get to the point where you're competent in teaching yourself. right? You learn how to teach yourself, because in the future, when you either you get your master's or your PhD, you're going to be new methods and the stuff for you to learn, and you figure out, you know, how to learn on your own because you've been through this process. So that's just my aside there. So we fit that model that I described, and we have the covariance parameters here. We have the variance for family, the variance for ID within family. We have the correlation, which is around 1/2. That's a day-to-day correlation. And then we have the residual variance. We have our fixed effect estimates. And we can see, for example, cold. I just have an indicator in the model. So if they had a cold, it's a 1. If they didn't, it's a 0. And I actually modeled that as I didn't put that in the class statement. So we're just going to have one column in for cold. And so what is this effect saying? It's saying that when you have a cold, there's an average increase in LT4. And that's not surprising because LT4 is a marker of inflammation. And so when they have a cold, they're going to be, the inflammation process is going to be exacerbated. So that's marginally significant. What is the date saying here, that date effect? So you're looking for the estimate, you know, and the p-value. We know that date is a continuous variable, right? So what is that telling us, just in general?
There isn't really an effect.
I'd say there's close to an effect. The 0.05.
Mm-hmm.
You know, don't get.
But your estimate is close to 0.
Yeah, but what's the thing? That brings something else that's important as well. Should we worry about that size of that estimate? That's, the slopes are dependent on the unit, right?
Right. So
Now, if we said this is day to day, but if we considered a month change, then how would we get that estimate?
Multiply by the month.
Yeah, exactly. So we multiply by 30, and it would look bigger, right? So, so you have to consider the units that you're dealing with. You may be right; it still may be small, but maybe going to a week or a month may give us a more meaningful estimate. It's marginally significant, but it's a linear. They're saying there's a linear increase in LT4 as time goes on. And why that is, I'm not exactly sure, but
I think it also depends on clinically, is it useful to look at the month scale or the day scale?
yeah.
If it's clinically useful to look at the day scale, then there's no effect because your estimate is 0.
That's a good point. What about temperature?
Is this the patient's temperature?
This is the outdoor temperature. So this would be like a warmer day versus a
Mm-hmm.
colder day.
And these are in Fahrenheit or in Celsius?
I think it's Fahrenheit. But again, just look at the direction of the coefficient and the p-value. So it's around 0.05, right? But what's the relationship between temperature and LT4?
Higher temperature, higher LT4.
Yeah, so there's more inflammation going on when it's warmer. Now, is it the warmer weather that's causing it? It's hard to say. It could be, this is just one possibility, but maybe they're going outside more when it's warmer and they're exercising, and that exercise leads to inflammation if they have asthma, right? So this is observational study data, and things that you have to keep in mind is that there could be confounders in there. That's possible. I don't know if the warm weather is directly going to affect their asthma, or it could be, again, it could be a confounder in there, like they may be going outside more or something like that. What about what we're really interested here in is whether there's correlation between family members? How can we test that out? Well, I don't think the best way is to look at these estimates, these variance estimates. What's an idea in terms of figuring out whether that whether there's dependence between siblings? We fit the model this way, right? Any other ideas about how to test?
So you can fit the model without accounting for the dependence, and then you can check the different model fits.
Yeah,
without-
good. That's it. That's how I did it, and that's a good answer. Like if you just fit the model without the family term, right? And we have, and then we can compare. In the simplest way would just be to compare AICs, right? And see if taking out family, and now we just have ID within family. And I kept everything else the same, but I took out that family term, and I look at the AIC here, and I get 444.6. So if we go back to the previous model, I think right here, it's actually higher when we had the 3-level model than when we had the 2-level model. So what is that telling us?
That the added complication is not necessarily producing better fit.
Yeah, that's right. So at least in terms of LT4, the dependence doesn't seem to be affecting our results too much. And maybe that's because, relatively speaking, there's not a lot of siblings, right? I mean, if we had large families and a lot of kids within families, and that was common, we might see more of an effect. It might also be because LT4 just behaves a little bit more independently when you're looking at kid to kid. My guess is probably more the first one, is that we just don't have a lot of siblings here. And that could be why we're not seeing an impact of accounting for sibling correlation.
I have a question, Matt.
Hey, Matt.
Go ahead.
Jonathan, go ahead first, and then Benjamin.
Could you possibly use this type of modeling approach for studies where you do have a bunch of siblings? And if you get a similar result as this, would you be able to justify that there's less of a genetic component in the results with the outcome?
It would be one way to do it. I think it would be kind of an indirect way to test that. Yeah.
Okay.
Benjamin, did you have a question?
Yes, I had a question. Most of the times when I've looked at the covariance parameter p-values and fitting different models by leaving, for example, family, you'll realize that the AIC and the p-values from these covariance parameters, they say the same thing. So for example, in this situation, if we look at the p-value from the covariance parameter estimates, it's insignificant. So we'll just decide to ignore it and fit the model without that.
Mm-hmm.
And the AICs will coincide. You'll find the AIC without it is always lower than the one with it, as long as the p-value is insignificant.
Mm-hmm. Yeah, that's true.
Why is it that?
Why is that?
Yeah. So is it okay if I just look at the p-value from the covariance parameter estimates and then decide if I want to leave it or not?
I personally, I'm a little more leery of p-values when it relates to covariance parameter estimates. You're right that in this case it worked out; they were consistent. One of the things that you notice for this example is if you look at those covariance parameter estimates, they're roughly the same order of magnitude. You have 0.05 and 0.06 in that 3-level model. And then what happens when you go to the 2-level model is that those get combined together. And so I think, I would say personally, I think the AIC approach, or maybe log likelihood approach, something that involves that, I would probably trust a little bit more than the p-values. Although I think you're right, in a lot of cases, they'll be consistent.
Okay.
So this is one way we can test for, sibling dependence or dependence between subjects. And that's pretty much the end of the slides, and I know we're basically out of time. So if you haven't yet, take a look at the homework and see if you have any questions, and we can talk more about that on Wednesday after class. Wednesday, we'll talk about a little bit more on nesting and crossing in hierarchical models. So thanks, everybody. We'll see you Wednesday. And Yanran, if you want to stay on, we can talk real quick. Hi. How you doing?
Good.
Okay, so you wanted to talk about the homework 3. Let me get that real quick.
Yep.
Oh, actually, I need to stop the